Hello to everyone. My name is Sergey Eyderman. I'm from Sergey Group, the previous speaker was. And today I'm going to be talking about light trapping and power conversion efficiency in thin film silicon and gallium arsenide photonic crystal solar cells. This is the outline of my talk. Basically, I'm going to be talking about the structure which was presented by the previous speaker. It's one of his last slides. And first, I'll tell you about optical and transport performance of this type of the structure. Then I'll switch to MEPD optimization and this type of structure for silicon solar cell. I'll clarify the role of anti-reflection and light trapping properties. And then I'll calculate the power conversion efficiency in silicon solar cell. And then the same type of result will be presented for exactly the same time of architecture, but in gallium arsenide solar cell. And it will bring me to the conclusion. So here briefly, optical and transport performance of solar cells. So we used FDTD algorithm in order to simulate the properties of our structure. In the frame of FDTD method, we solve Maxwell equations, and then we get the absorption coefficient according to this formula. So it gives the absorption at each point of the computational mesh inside our structure. And in order to get the full absorption, frequency dependent, then we'll just integrate over the whole volume. And the MEPD we get according to this guy. So we integrate the absorption we obtain in the frame of the FDTD algorithm, the solar irradiance spectrum, and we get an MEPD. In order to obtain the efficiency, the power conversion efficiency of our solar cell, we solve basic semiconductor equations, probably both of you are familiar with. And the structure, basically, before I start talking about my structure, I would like to give you some reference number. This is the result of the simulation of just the power conversion efficiency of planar silicon solar cell with the thickness of 1 micron with the surface uniform surface recombination of 10 to 3 centimeters per second, depending on the diffusion length. We see here that the diffusion length more than 10 microns, it saturates and it reaches just 5.1%. The structure I'm going to be talking about today, this is crystalline silicon sculptured into the form of slanted conical pore photonic crystal. It's presented here, and on this left panel you can see two mechanisms of light trapping. So these guys, they represent the so-called parallel to interface energy flow, and also some vorticity, which I observed as well, and which previous speaker was talking about a few minutes ago. So this is the result of, this is an attempt to manufacture actually this structure by our colleagues in Australia. And on this slide, on the right panel, you see the result of MEPD optimization itself. So it's basically, it was for this sort of structure, these slanted conical pores inside silicon. This is region number 2, this is silicon, and 1 is infinite glass substrate, and cones in this case are filled with air. And you see that the MEPD in this case reached 25.5 milliamps per square centimeter at the optimal parameters radius of the cones, 500 nanometers, and lattice constant equals to 850 nanometers. But if we add silver back reflector in order to reflect the whole radiation back to the structure, and if we integrate from 300 up to 11,000 nanometers, then we can get an MEPD of 35.5 milliamps per square centimeter. At this picture, I presented an MEPD dependence on the overall depths of these nanopores, basically for this type of structure. In this case, this structure is encapsulated with silica, and it corresponds to this green curve. We see that it behaves a little bit worse compared to the blue curve, which we obtain in the case of just air filling of this structure. But the drop in the MEPD is not such tragic, I would say. So it just it gets about 34 milliamps per square centimeter. But the maximum MEPD we obtained, again, it's for air fueling, and it corresponds to 35.5 milliamps per square centimeter, and it is almost 85% of all available sunlight in the specified wavelength range. So here we compare the absorption spectrum for these optimal parameters with the so-called ray trapping limit, which is presented here by this formula, probably you're familiar with as well. So our partial MEPD, calculated in the near infrared range from 850 up to 11,000 nanometers, so gives us an MEPD of almost 11 milliamps per square centimeter, while partial MEPD inferred from this formula and with the underlying assumption intrinsic to ray trapping gives just 7 milliamps per square centimeter. Why it occurs? Because we can't ignore the wave nature of the light in this region. You see here very strong absorption peaks where the intrinsic absorption of silicon is really weak. So in order to elucidate the nature of these peaks, we plotted exactly at these wavelengths, which correspond to the maximum of one of those peaks. We plotted Poynting vector and energy density distribution for this structure in the slice shown in the inset. And as I said before, for the first mechanism of light trapping, this is this sort of vorticity you can observe. So I just zoomed one of these areas here. And also this is parallel to the interface energy flow, which as well increases the dwell time we estimated it as about 30, maybe 40 times compared to just a planar cell. So, and it gives rise to these very strong absorption peaks you've seen on the previous slide. And also I have to mention very strong intensity amplification. You see these dark spots compared to the impinging pulse, and you see that the factor of amplification is about 100 here. Here I present the power conversion efficiency dependence from diffusion lengths for this type of structure. And you remember this reference case 5.1, but we can achieve 17.5 for slanted conical pore structure and 22.5% as well, depending on the surface recombination. So next part of my talk, this is MEPD dependence, basically the same structure, but in this case, this is gallium arsenide. The major difference here that it's just 200 nanometers gallium arsenide photonic crystal compared to 1 micron previous thickness. And here you see the result of optimization. Again, this structure rests on a silver substrate. It encapsulated with air in this case, and we can obtain the MEPD of 27.5 milliamps per square centimeter, as you can see here. But if we add certain modifications as aluminum gallium arsenide layer or also some passivation, then we can obtain a MEPD of 27.8 milliamps per square centimeter, which corresponds to almost 90% of all available sunlight. And here so I present an IV curve for this type of structure, and we attain a remarkable power conversion efficiency. Using only 200 nanometers, we obtain 28.3% with open circuit voltage of 1.12 and 27.8 of MEPD. And it happens at surface recombination of 10 to 3 nanometers. And this is actually comparable to the current world record of single junction solar cell efficiency obtained by Alta devices with 3 microns effective bulk thickness of gallium arsenide, which uses, as you can see, 15 times more amount of material. So this number brings me to the conclusion. I calculated the MEPD for 2 types of slanted conical pore structures. For silicon, we achieved an an MEPD of 35.5 milliamps per square centimeter, and at recombination of 100, we achieved 22.5% of the power conversion efficiency. For gallium arsenide, using only 200 nanometers equivalent bulk thickness, we achieved an MEPD of 27.8 with power conversion efficiency of 28.3%, which is comparable, as I said before, to the current world record, using only 15 times smaller amount of gallium arsenide. Thank you very much.